Okay, so now we can start. Currently, we are in the week 6 and in the technique of material characterization course. So before I start with the discussing the doubts and discussing any content which I am prepared for today, I made few questions and concepts. Before that, I would like to ask you that do you have any doubt which you want to clarify with me? If yes, please feel free to unmute yourself and interact. If not, then or also if you want, you can also put in the chat box. So feel free, whatever you prefer, it will be fine with me. Okay, since there is no doubt, we can start with the today's this week doubt solving sessions. So the topic that we have covered in this particular week is as follow. We discuss to certain extent the remaining part of the X-ray absorption, where we again try to go in more detail about the cage, and we saw that how we can eliminate the K beta and also how we can eliminate the continuous X-ray. So our aim was to eliminate this thing. Now, next part we discuss about is the intensity of the diffracted beam, which is which was depending upon the how the interacting X-ray is going to be it's like the incoming X-ray is going to interact with the electron, then how it is going to interact with an atom, and then how it is going to interact with a unit cell. Right. This thing we just started the last video, which we just started, where the derivation and all you might have saw, but it's not completed yet. So we'll discuss to certain extent this, but the last part which professor had discussed, I would prefer that if we discuss that part in the next week because the some part of that it's still remaining. So these are the list of the content that we have covered in this particular week. If you have any question, any doubt in this particular content, please let me know. We can have a detailed discussion on that. Before I proceed further. Okay, since there is no doubt, let's move ahead. We'll try to see few concepts and based on them, we'll try to solve couple of questions. So here in the last class also we saw that how the continuous X-ray and how the characteristic X-ray are going to be produced. Their production we have saw, and we also saw that the K alpha is there and K beta is there, right? And among the K alpha, we also know that it's again a doublet, which is K alpha 1 and K alpha 2. Okay, which we are not able to separate. So we cannot separate them. So no matter what filter you use, you cannot separate them because their energies are very close. While we can separate the K alpha, K beta, K alpha and K beta and continuous X-ray. These three we can separate. We can eliminate the continuous X-ray, we can eliminate the K beta, and we can make sure that our specimen, so our X-ray is only consisting about the K alpha. Okay. So now, how we have done? So these are the characteristic X-ray that we have generated, and this is the broad spectrum. This is the continuous spectrum, right? So with increasing the voltage at which our X-ray is operating, at which the X-ray tube is operating, we can increase the intensities of this continuous X-ray, and so also we can increase the intensity of the K alpha. Initially, it was not even appearing K alpha and K beta, but later on, if I increase like from the 25 kV, if I increase to the 40 kV, the intensity will further increase. Okay, so this was the content about the production of the X-ray. Now, every material. Now, let's say we want to understand that how X-ray is going to interact with my material. Let's say our concern is right now, this is my material, and I am passing an X-ray through it. The thing which is going is X-ray. Now what and all it's going to happen? Okay. So my material, once the intensity, some intensity will come out. Let's say this is the I, and incoming intensity was I naught. So what and all are going to happen? So here it's telling that if I pass, see on the x-axis what is there? On the x-axis we have wavelength. So wavelength is in this direction. Now since the wavelength and the energy, they are inversely related with each other, E is hc by lambda. So we can say that in this direction we are increasing the energy. So if I keep on increasing the energy of my beam, the absorption will keep on decreasing. On the y-axis what we are having is the absorption, mu by rho, right? This is absorption. So the extent of absorption, which was happening as 2.5 wavelength, will decrease as we keep on increasing the wavelength. It means that as we are increasing the energy, our absorption is keep on decreasing. This is very similar analogy. You can take that, okay, you are passing some ball or some beam with a high energy, so it's the ability of the material to absorb will decrease because the energy is very high. For example, you took a ball in your hand and you try to throw, and your aim was to break the ball. So break the ball. So in that, what we will do, if you throw the ball with a very high speed, so your ball will not be able to sustain that much energy, and it will break, and the absorption will keep on decreasing. So now a material was keep on decreasing the absorption, but a point will come when, let's say this was the nucleus and this is the electrons are there. Now what will happen that from the K cell the electron will be ejected. You supplied the energy has increased to the sufficient level. Let's say over here the energy has increased to sufficient level which can eject this particular electron, and now so what all the energy that you are supplying will be absorbed in the this removing the electron from the K cell. Okay. So your again the absorption will be very high because all the energies which you are giving to the material it's absorbing in producing this particular effect, where again you will see the fluorescence phenomena and photoelectron will be there. Okay, electron will be generated because of because it will knock out, and the X-ray will also be emit because of the energy difference between the L and K. Okay, which will try to minimize the entire energy. So if I keep on increasing the energy, a critical point will come where the all the things is going to get absorbed. So this is how it is. So this is a K absorption age. Okay, so this is what is known as the K absorption age, where the, the energy at which the particular material, whatever you are using, let's say here the thing which we are talking about is about the nickel. So every material will have a fixed K absorption age, like it means that they have the fixed wavelength, right? So this is all the discussion that I wanted to make right now. So let me know, is there any doubt in this particular thing that we have discussed till now? Okay, since there is no, let's move ahead. Let's try to solve a couple of questions. Yes, sir. Uh, Ahmed, you are not audible. Can you speak little louder to remove the K beta? Right. Yeah, yeah. Yes, sure. So, which filter we are going to use and how it is the intensity is going to change between the K alpha and K beta. I have prepared one more content after we solve a couple of questions. We are going to that part. So we'll discuss. We are. I planned that we are going to discuss those things again. Okay. So we'll answer those questions, your doubt during that time. So now let's try. Yeah. 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 Uh, yeah. So even if we remove, so let's say let's analyze the question. So this is my nucleus. Let's say this is K cell, L cell, M cell, N cell. Okay. So even if I let's say even if I remove the K, let's say I remove the K. So now what is happening that the K cell electron I removed, this electron I removed. Now what is going to happen? The transition from L to K will happen. So what it's going to do? It's going to say that the electron is jumping from the L to the K cell. So what it result? It also result in the hole in the L cell. Now again the cascading effect will be there. Now M cell from the electron from the M cell it will again come over here. Electron from the N cell will also come over here. So you are exactly right that we should get the entire spectrum. So let's try to draw it. Let's say this is my K alpha and this is my K beta. Okay. So K alpha and K beta I'm getting this from this to this and from this L to K. Okay. So now what is happening that the remaining energy which we are having, see this much energy was sufficient. This is a large energy. Correspondingly, it will have the smaller wavelength. And this wavelength will be, which we talk about 1.54, it's very beneficial for us to characterize the specimen to find its structure. Now the energy here is decreasing. Energy is keep on decreasing. Okay. So it means that the wavelength will definitely increase, so on and so forth. Also, the thing is that statistically at quantum level, this particular transition from L to K is preferred. So they are more in number. The number is more. Okay. So their number is more. They are more in intensity. The count will be more and more, which will not be in the case of this ML and this. Okay. So and overall energy is also less. And it is very easy. See, you can see we are only concerned about the K alpha, the most intense peak that we are getting in the entire this transition which is happening. So we are only concerned about the K alpha. The reason is that here that remaining intensities are very low. Remaining all the intensity which we will get, they are very low, and it's very easy to filter them. We can remove them easily. So our concern, see, in our material, multiple things are happening. So let's say your concern is that okay, why not let's use the K beta. Okay, let's say we are ready to use the K beta, but we won't be able to eliminate the K alpha in that case. In the process of eliminating the K alpha, you will end up in the situation where you completely eliminated the K beta. Okay. So what we are taking the most high intense peak, high intense X-ray, which are generating, which is more in the count and which is more in the intensity, so on and so forth. And we are characterizing our material with this. Now, how we can see? We can remove this continuous X-ray. We can remove this with the beryllium window. So last time we saw that what we discussed is that there is an anode and cathode, and there is a from here from the target material. When the X-ray will come, they will go from somewhere over here. So here what we are having is a beryllium window. Now what this window will do, it will absorb the entire continuous X-ray. To a certain extent, it will also decrease the intensity of the K alpha and K beta, but still the ratio of the intensity of the K alpha and K beta, the K alpha will be on the higher side, quite higher side. Now, we remove, using the Brilliant window, we remove the continuous X-ray, we are left with the K beta and the K alpha. Now to remove this, to separate this, to make our beam monochromatic in nature, what we have to do? We have to eliminate the K beta. Because we know that the K alpha is more in amount. Something is which is in more in amount, you cannot eliminate that. Okay. So now if we try to eliminate K beta, which will be, we will do by nickel filter. But how it is done? How it is done, that is something which we are going to discuss in the upcoming slide which I have prepared. Okay. So this is the entire thing. Okay. Yeah, that's great. So now let's try to solve a couple of questions which we have prepared. Okay. So now here what we can see, I hope the concept of K is there, and the how the continuous and the characteristic X-ray has been produced is clear. And here we talk about the different transition energy level which is going to occur in our specimen. So now let's talk about this. What is the primary reason for the sharp increase in the mass absorption coefficient at the K absorption edge? They are asking that what is the reason for this to occur. For this one. So on the x-axis we have lambda, on the y-axis we have mu by rho. This is absorption. This is the extent of absorption which is happening, and this is the wavelength. Okay. So now they are asking that, the question is that why this sharp sudden increase is there. Okay, why this K absorption is there. Question, the first option, a decrease in the scattering event. Second, incident X-ray energy is used to eject the K cell electron, and that is where it is getting absorbed. C, the X-ray photon gains sufficient energy to pass through the material without interacting. So no interaction, they are telling that, okay, they have sufficient energy, then they are not going any interaction. D, the characteristic fluorescence radiation is reabsorbed by the material. So what do you think? Among all this, A, B, C and D, which one is the right answer? Yeah, very good, Gitu. The right answer is option B. Right? Everyone agree with that? So what is happening is that, again, we had the nucleus, we had the K cell, we had the L cell. K cell was having the electron. Now our energy of the incoming X-ray, this is about, we are talking about the X-ray. So no need to get confused with the electrons, and we are talking about the X-ray. Now the X-ray came. Now it is interacting with the material, and it saw that, okay, it has a sufficient energy. The energy was so high that it can knock out this particular electron and remove it. So now the energy of the X-ray is getting absorbed in this, removing the electron, and that is why this jump is there. Okay, very good, guys. So the right answer is option B over here. Okay. Any doubt in this entire discussion, which whatever we are making, at any point you feel like there is some confusion, please stop me at that time. Okay, we'll have a discussion on that. Let's go to the next question, question number 2. So now, yeah, this is very interesting part. The question is that what is the relationship between the wavelength of the K absorption edge and the wavelength of the K characteristic radiation? Okay, so that is K alpha for a given material. So now we have to talk about two things, K absorption edge, and again second thing, K characteristic radiation. Okay. Now see, you are passing an X-ray through the material. Let's say this is my material is there. You are passing an X-ray. Now this X-ray is going to do two things. First of all, since we are talking about the K edge and K characteristic it's obvious that we are talking on this particular region. Okay, so now in this particular region, let's say my X-ray has the energy E X-ray, which it is going to transfer, it's going to knock out this particular electron which is near to the nucleus, this electron which is there to the nucleus, it is going to knock it out. Okay, so and the energy transition will occur from here to here, L2. And now the what is happening that once this electron is knocked out, this electron will try to leave the specimen, or it will try to go to the higher energy states, so it will have some kinetic energy. It's like a photoelectron which we are seeing. So there is a two thing which is happening, that what the first effect is that X-ray phenomena is happening, that the fluorescence, this is known as the fluorescence phenomena, which like from the higher energy state to the lower energy state, so energy is consumed in the fluorescence. Second thing which is happening, that the is a photoelectron. Right. So now the amount of energy that is needed, so this is the amount of energy which is absorbed, right? This is the amount of energy which is absorbed in causing this two effect. So energy, so can I write, let's say, can I write that from here E X-ray will be greater than energy required for the fluorescence phenomena? Everyone agree? Because now I'm removing this particular term, let's say. So can I say that since it was addition, the left hand side, the term will be greater than the right hand side term, right? It's simply like if 5 is equal to the 3 plus 2, so I can say that 5 is greater than 3. Simple. So now from here we got that the amount of energy that is been required, that will be absorbed in the material, will be greater than the amount of energy which is produced in the X-ray, like to produce the phenomena of fluorescence. Okay. So now from here, from these two things, we know that the energy is inversely proportional to the wavelength. So from here, can I say that the lambda, which is X-ray, will be lower. Now the sign I will reverse, will be lower than the wavelength for the fluorescence phenomenon. Right. Now this is the amount of energy which is absorbed. That's why we are calling it the K absorption. Okay. So now this is related with the absorption. And now this is the radiation part, that it is related with the fluorescence. So when I draw, let's say when I am drawing this particular thing, so my this particular, the second one, this is the first one, let's say the second wavelength is higher, so it will on the x-axis we are putting the wavelength, so that it will correspond somewhere over here, the second point, while the K absorption age will be somewhere over here, right? So they are the two different phenomena, right? This is the phenomena, this is telling that the how much X-ray has been absorbed, this is talking about the how much has been absorbed, how much, and this one is talking about the how much X-ray has been reproduced, that is how much fluorescence phenomena is happening. So this is how much fluorescence phenomena, how much like what is the energy of the fluorescence of the X-ray, and this is the what is the wavelength corresponding to which the absorption is happening. Okay, so this thing is clear. So now let's try to answer this based on the concept that we have learned. So we have already answered this particular question. Can anyone just write among A, B, C, and D which one is the right answer? Very good. So so this is corresponding to the X-ray. So it's a lambda K, and this will correspond to the lambda K alpha, right? So the right answer here is option B. Okay. So I hope this is clear. If not, please let me know. We can discuss it again. Okay. Since it's clear, let's move to the next part. question is true and false. For a given element, the mass absorption coefficient decrease monotonically, telling that it will just keep on decreasing. Mu by rho will just keep on decreasing as the wavelength of the incident X-ray is decreasing. The emphasis over here is monotonically. What do you think? Is it true or false? It will just continuously just keep on decreasing, or somewhere it will increase. Lambda is nothing but we can relate it with the energy increasing. If more energy is there, if it keep on increasing, it means that the absorption will keep on decreasing. But we also know there is a point. But before that, can anyone answer, like, is it the true or false? It's false, right? Very good. So we know that even though it was keep on decreasing, even though mu by rho, if I'm decreasing the wavelength, what is happening that the absorption is keep on decreasing, but the point is coming where it will have a sharp increase, right? So the sharp increase will be there, and this is the reason why answer is okay. Great. So with that, we have solved these three questions. It was completely the concept of KH. Now let's go ahead. Let's try to answer the next part, which has asked us. Now we are talking about the filter. We are going to talk about how we are going to separate K alpha and K beta. Okay, these two we want to separate. We don't want two wavelengths to exist in our X-ray. Okay, so we want to eliminate any one of them. It was easy to eliminate K beta. That's what, and how it is happening is something which we are going to see. Now, just now we discussed about that the KH. What we saw that it was keep on increasing, like it was the radiation was something like this. I made it little bit wrong. I should have made it little bit more gradual. Yeah, okay. So this is how it is. So we know that this is the edge, this is the lambda, and this is the mu by rho over here. Now, can anyone, so this is so this one, let's say we'll consider 2 points, point number 1 and the point number 2. So which one, what do you think, which point is having more energy? Point 1 is having more energy, or point 2 is having more energy? So Ahmed, it will be, I want you to answer this, like, which one is having more energy?
Having wavelength is increasing.
Yeah.
The energy is opposite direction. Yeah.
So point 2 is having more energy.
Yeah.
Great. So now one more question I have for you, that let's talk about that the K alpha and K beta. Which one is having more wavelength? Or you can also answer that which one is having more energy. So this was a transition. This is my nucleus.
Alpha having more wavelength, less energy. K alpha having more wavelength, less energy.
Okay, so the K beta is having more energy, right? So now K beta is having more energy. Now I will try to place, I had the material, so we did the X-ray, like we got an X-ray, X-ray was having the K alpha and K beta, and I found that okay, they were having the different what we can say energy. So correspondingly, as you guys have said that lambda of k alpha will be more than the lambda of k beta, right? So now let's say lambda, if I try to place somewhere over here, if I try to place this particular wavelength, so k beta was having the lower wavelength, so it will correspond to somewhere the point 2. Okay, so this will be the k beta, let's say, and the one will be the k alpha. K alpha was having more, right? This is the k alpha, and this is the k beta. So now what is going to happen? Till now we see, we very smartly we have to pick this material. This material is nickel. Okay, the radiation which we are talking about is a copper k alpha, copper k beta, and all those things. So nickel k is lie between, this k is lie between k alpha and k beta. We will never pick a material which is like this, whose k is something like this is the k alpha is over here and beta is over here. This case is not preferred, and neither this case is preferred. Okay. This is not preferred. We have very smartly we have to pick up a material whose k edge will lie in between the k alpha and k beta. And now we can understand these things that let's draw again. Let's draw. I'm just going to draw this diagram again. So initially, say the before the filter, before without filter, their intensity was like this. Okay. Okay. Before filter. Now here, A beta is just like on this side of the cage. There, that's also quite higher. But here the alpha is somewhere over here. Correspondingly, whose absorption is quite low. Right? The K beta absorbing is more. The K alpha is less. So what means that the K beta energy will be absorbed more. So what it means? The K beta will be used in the material in this filter. We will be discussing about the nickel filter. In the K beta, K alpha will also absorb, but we can see that. So initially the ratio was like that. So but after the filter, what will happen to the intensities? They will be like this. In certain cases, it happens that the intensities will be small and this will be so much high. Okay, so much high. Okay. Pardon for a bit. I don't want to draw this bit. It's very sharp. The things will be very sharp. Okay. So this is how. So this is the effect of filter. It selectively absorbs K beta more compared to the K alpha. Okay, is it clear? So is this part got clear to you? The question which you had on the absorption. Okay. Since there is no doubt, now we can go ahead. Let me please. So with that, we discuss about that how the absorption is going to happen, how selectively we can eliminate K beta with respect to the K alpha, and after what we can say the nickel filter, we are getting the only the K alpha. We can follow that schematic that okay, initially we were having the K alpha we had the k beta, we were having the continuous X-ray. Okay, we pass this through the beryllium window. So what we got from there, we got k alpha and we got k beta. This we pass through the nickel filter, we got k alpha. Always remember, when I'm writing that thing like the continuous X-ray is eliminated, some fraction, small fraction will still be there. If anyone asks that 100% are we able to eliminate, answer will be no. Even the k beta here will be very small. It will be negligible, that it will be like somewhere in the background. So when you do the elimination, so the elimination is never 100%. It might be possible that the ratio between the k alpha and k beta can be like this. This is k alpha, this is k beta. Okay, at the end. Okay, so this is what all I wanted to discuss from this filter perspective. If any doubt in this entire explanation, please let me know. If let's move to the next part. We'll try to solve a lot of questions. Now here, what is the main trade-off when using an X-ray filter? A, it improves the directionality of the beam but reduces energy. B, it reduces the pure monochromatic beam but significantly reduces the overall intensity. Monochromatic significantly reduces the overall intensity. It eliminates the current spectrum but introduce new characteristic line, stating that a new characteristic will be introduced. It increases the resolution but requires a more complex experimental setup. What do you think? What will be the right answer over here? They are asking that what is the main trade-off of using this particular filter? Initially, K alpha was having this much intensity. After the filter, K alpha decreased. K beta also decreased, but K alpha decreased less and K beta decreased far more. Okay, K beta decreased too much, and this is why we are able to produce the monochromatic beam. Like monochromatic beam, we are able to produce. But the only trade-off is that the intensity, the count of the K alpha is not decreased. Okay. The right answer here in this entire thing, A, B, C, and D, like that, even though we are able to produce monochromatic beam, but we are significantly reducing the overall intensities. Okay, so the right answer is option B. Okay. So any doubt in this, guys? Let me know. Okay. While analyzing the XRD, we do strip K alpha. Is it to remove other ray K beta? Okay, you're talking about that. I got it. Whenever you see a peak in the XRD pattern, like you see something like this. If we zoom particular region in X-ray, it will look something like this. So this is corresponding to the K alpha 1 and K alpha 2. Whatever the instrument, wherever you have instrument, so they will among these three things, you will only have the K alpha. But the problem is the K alpha is that it is still a doublet. It is having the K alpha 1 and K alpha 2. These two parts. In the last week, we discussed that they are, you see that their wavelength, it's around like in the fourth digit of the decimal. When you're talking the Armstrong perspective, they are changing. Their energy is very close with each other. And so that's why we are doing the strip K alpha. Okay. So the software, whatever you try to analyze, it has to deal with the K alpha 2. It try to eliminate the K alpha 2. Once you do this, you try again, you see in your software, what you will see is that you will see something like this. Okay, if you zoom this region, you will see like this. If you do the strip K alpha 2, you will get it over here. So it will try to, mathematically it will try to eliminate this K alpha 2, which is experimentally is not possible to remove the K alpha 2. You can just mathematically try to operate that how the K alpha 1 peak is based upon the mathematical the models which is available. It usually take the mixture of the Gaussian and white pseudo white functions. Okay, so these things this is what it is from the K alpha stripping K alpha perspective. Okay, is it clear? Okay, great. So now we can move ahead to the next question, question number 5. So now this part we have discussed in the class. The professor has mentioned this particular the concept on this material itself. It's just that we are going to revise whatever the professor has explained to us. So let's say we are having the copper target. Target is from where we are going to generate an X-ray. So we will get the copper K alpha. You will get the copper K beta. Right. Now, for a copper target, what filter material is typically used according to the thumb rule mentioned in the lecture? Okay, we discussed in the lecture, that's why I wrote this part. So the thumb rule is that whatever is your target material, brightness is too much, I think. This much is fine. The thumb rule is that whatever is your target material, whatever the Z number it having, just subtract 1 from that, and that will be your filter material you should take. So that's the reason you can see that for the copper, which was having the 29 atomic number, we choose the filter to be the nickel, which is 28. Right. So the right answer over here is the option. Okay. And the reason is very simple. The reason is that is this only, that if you take the Z just below this, the target material, your K edge going to lie between K alpha and K beta. Between this only K edge will lie. Right. Similar type of questions you will get in the assignment. You can solve them very easily. Okay. So this is the entire thing that regarding that absorption part. Let's try to answer one more question. It's a true or false again. The characteristic K alpha radiation from an X-ray tube is perfectly monochromatic and does not require filtering. What do you think? From the X-ray tube, what we are getting is a monochromatic. The question is saying that from the X-ray tube which we have got is a monochromatic. The answer is false here. Now, whatever we are getting from the X-ray tube is having the beryllium window also. So we are taking, okay, the continuous X-ray has already been reduced to very large extent. So what we are having left is K alpha and K beta, which is not monochromatic. Okay. Now, even if someone asks you, now is the K alpha is a monochromatic? Is this is a monochromatic? The answer will be no. Still, it's having the K alpha 1 and K alpha 2. Right. Our aim is to get a monochromatic, but we are not getting. But we are removing somehow. We are remove the K beta. So the right answer here is false. Okay. So this was the entire thing about that the KH and the K absorption part. So from here onwards, we are going to discuss about the diffraction, the thing that we have started in this particular week. The next part of our discussion will be the absorption. Okay. So let's discuss this part. Now, see, the X-ray now we have got K alpha which is having the doublet K alpha 1 and K alpha 2. Now, how it is going to interact with the material? Okay. Now we discuss about the absorption, K absorption and all to filter the X-ray. From here onwards, whatever we are going to discuss is with respect to the K alpha. Okay. Now, the K alpha, this X-ray is going to the material and how it is going to interact. So your X-ray will first interact with an electron. The collection of electron will see that we'll see from the summation, like how we'll see that how one electron is in an X-ray. Then we see all the how the collectively is going to. So we'll see that the how atom is going to interact with it. From here, we'll see that the how unit cell is going to interact with the X-ray overall. Okay, so this is our aim. Yeah. So we discussed the two things. There is something known as Thomson scattering and one thing known as the Compton scattering. The Thomson scattering is the one like see X-ray is a X-ray is a electromagnetic radiations. It is having the electric field, something like this, right? Now electron is also a wave. So now two wave is going to interact with each other, right? So what is going to happen that electron, once it get in the presence of the field, we know that it will accelerate and it will decelerate. Okay, for a timing it can accelerate if their waves are matching. If not, if they are opposite, they will decelerate. So we know that the electron, once it come in the effect of the electric field, this is the phenomena is going to happen. Now, what is electron is doing? It is absorbing that particular energy, and then it is releasing that energy, right? So this entire process is the frequency at which the frequency of your X-ray, whatever is the frequency of your X-ray, the same frequency the electron will also vibrate, and the same frequency it is going to eliminate. It will radiate. Okay, so we are having the electron, we pass an X-ray to it. Now it's going to irradiate. Okay, so the thing is that whatever was the energy of the X-ray, the same energy will be of this radiated X-ray will be there from the electron. Okay, it's just like a mediator. It's working like, okay, it's like you are taking something from one person and you are distributing it to the multiple person. Because now, why I'm saying the multiple person, because the direction are different. At different direction, electron will scatter different. Okay, it will give to the different direction. The scattering will be in all the directions. So now, here the thing is that their energies are matching. It means that their wavelength is same and also their phase is same. Okay, so they are coherent. So Thomson scattering is a coherent, and like that is they are in the same phase and they have the same wavelength. Okay, so this is about the Thomson scattering. Also our X-ray can interact with the loosely bonded electrons on the higher energy side of the atom. Those can lead to the scattering of the X-ray. Okay, and the X-ray, the characteristic value which was happening. So there is something known as the Compton scattering. Here, the X-ray is going in the inelastic scattering. Here, in the Thomson scattering, here it was elastic. Right. Here it's the inelastic scattering. Now, since it's the inelastic scattering, that is there, and the X-ray, the characteristicness which was our X-ray was having, it is going to lose. The energy will spread. The spread in the energy. This is going to contribute toward the background of the X-ray. So sometimes you see that the background is quite high, sometimes you see the background is quite low. This has something to do with the the Compton scattering. Okay. So this was regarding the Thomson and Compton scattering. This is how the electrons are going to interact with our X-ray. So now here, so multiple atom is having multiple electrons. So now if we this is an incident X-ray, it's going to interact with this. So the summation of all these things and at particular different angle. Okay, here we can say it's a 2 theta. So theta, as we keep on changing, the intensity will also keep on changing. So this is the equation which tell us how the intensity is going to change. Okay, theta is the angle, r is the distance, and k is a constant, I naught is the initial intensity, I is the intensity at particular point. Okay, so now let us say, so when I am getting the highest intensity, IP, when it is maximum, at what value of theta the IP is maximum? Can anyone answer this? At what value of theta the IP is maximum? Very good. The right answer is 0. That is when it is transmitted, right? When there is the theta is coming to be 0. As we are moving away, as the angle are keep on increasing, we can see that the intensities are further decreasing. Okay, this is what it is happening. You will also see in your XRD plot that as you keep on decreasing the theta, as you keep on increasing the theta, what you are seeing, the peaks will have lower and lower intensities. Okay, this is also like, it's also again going to it will add up. The things is going to add up. So now till now what we discussed about the electron and about the atom. So this was about the atom, how an entire atom is going to interact. So the intensity you are getting from an atom will be something like this. So now over here we can say that the amount of scattering that you are getting from an atom, it's an atomic scattering factor. We call it to be the atomic scattering factor. It's very important whenever we are talking about the diffraction. It will come even the electron diffraction, TM, SEM, and like whenever you talk about the EBSD, structure factor still also be there, and also in the X-ray is very important, right? So now atomic scattering factor, what it is? It is a ratio that what is the amplitude of X-ray scattered by one atom. Okay, what is the amplitude of an X-ray scattered by one atom divided by the amplitude of X-ray which is scattered by one electron. So it's a ratio how much is atom is scattering to how much is the electron is scattering. Okay, so this is what it is. Now let's try to solve a couple of questions based on the thing that we have learned over here. So what is the fundamental reason that Bragg's law? Okay, should we answer this now or should we answer it later? Okay, we'll answer this question number 7 at the end. Now here, in Thomson scattering, the scattered X-ray beam has which of the following property related to the incident beam, incoming beam? Thomson scattering. What do you think? So now we are discussing about the Thomson scattering. Giru is saying that option B is the right answer. That's very good because it's a coherent, right? And the wavelength is not changing, energy is same, right? So the right answer is option B. So Thomson scattering, which we are going to discuss in the X-ray, where we are talking about the diffraction phenomena. Compton scattering is the one which is going to be created which is going to create the background part. Okay. One more thing I would like to tell you that this Thomson scattering and all which we talk, like it's a sine theta by lambda, like F is increasing, F is decreasing as sine theta by lambda is increasing, right? But for the Compton, this is for the Thomson scattering. Let's say for the Compton scattering, if we talk, so the F will increase if sine theta over lambda is going to be increased. Okay, it will have a positive effect over here. Okay, it's a positive effect. So whatever is the answer you will think for the Thomson, it is opposite for the Compton. Now let me ask you, if I'm increasing the Z, atomic number I'm increasing, it means that the Thomson scattering I'm increasing. So what do you think? The Compton will, in that way, the Compton will decrease. If I'm increasing the Z, Thomson will increase, Compton scattering will decrease, right? So this is these are the again one thing that we have discussed in the class. So we should remember this part. Okay, very good. Let's go to the next part. Next question, question number 9. How does Compton scattering differ fundamentally from the Thomson scattering? Compton scattering is an interaction while Thomson is an inelastic. Compton scattering produces a coherent beam while Thomson produces a coherent beam. Compton scattering is an inelastic interaction that changes the wavelength of the X-ray while Thomson's is elastic. They are same. Okay, Gitu is saying now option C is the right answer. Very good. So the Compton is an inelastic and the Thomson is elastic. Right? This is what we have discussed till now. Very good. This was the question number 9. Let's go to the question number 10. In which direction is the atomic scattering factor for an atom at its maximum value? Okay. In which direction? So we are talking about the theta. At what value of the theta you are going to get the maximum, the value of f? What do you think? We have discussed this just now, a couple of minutes back. You guys have already answered. Yes, very good, Ahmed. Yeah, very good, Gitu. So here we can see that if it is straight, then it will be having the, in the forward direction we are having the maximum theta, right? Very good. So let's move ahead. So now let's try to answer these things. I have already discussed. I want you guys, everyone, to answer this. The atomic scattering factor f increase with. So now, under what condition f is increasing? Let me tell you one thing. It can be more than one answer can be right over here. I'll wait for the answer. Please let me know. We know f depends upon things z, theta, and lambda. Among this, which one will be the right answer? We want to increase the, our aim is to increase the f. Ahmed is saying that A, very good, then we have to increase it, and B, decrease the wavelength. So if I'm decreasing the wavelength, okay, let's see this part. If I'm decreasing the wavelength, lambda is decreasing, to this, it means that this entire thing is increasing. It means that the f is decreasing, right? Yeah, very good, Chandrani. The answer A is the right answer. So yeah, so it's not the B, it's a C, right? Increasing, sorry, the right answer is only option A. Okay, okay, I thought I am going to make it MCQ, but I end up making it only one. Oh, so only answer A is the right answer. We want to increase the f, right? So see, we know that f will decrease. Okay, sorry guys. I think I made a mistake. We want to increase the f. F is sine theta by lambda. If theta will decrease, if theta will increase, it means that this f is going to decrease. If lambda will decrease, if lambda is decreasing, it means that this entire term is increasing. It means that the f is decreasing. So if I want to increase the f, I should increase the wavelength, right? So the wavelength should increase to increase the f. So it should be like, okay, instead of decreasing, if I would have write the A, if I would have write the increasing, so B will be the right answer over here. Okay, so guys, very good. Yeah, Chandrani has put the correct answer. The answer is A. Right. So increasing the atomic number. Let me know, am I making any mistake or what? Or the right answer is A. What do you think? Just think again. It's simple, no? F depend upon sin theta over lambda. Sorry, it not. F inversely depend upon this. So what we can say that it directly depend upon lambda over sin theta. So if I'm increasing the lambda, it means that I'm increasing the F. If I'm decreasing the theta, it means that I'm decreasing this entire thing. I'm increasing the entire term. It means that I'm increasing the F. Okay, right. So this is what it is. So R is to increase the F. RM is to increase the F. How we can do? One, we have already know that to increase the F, we have to increase the Z value. So here the first is right. Second is telling that decrease the wavelength. Should we decrease the wavelength or increase the wavelength? So option B is also wrong. The third part, we should decrease the theta, right? So sin theta will also decrease. So F should, right? So again, this is the wrong. So none of the above is also wrong. The only right answer is option A. Okay, very good, guys. I think it's clear. If any doubt in this, let me know. I should have framed it. If I would have framed it instead of increasing, if I would have framed it decreasing, then two things will be right answer. Then it would be MSQ. I made a mistake while making question. Okay, let's go ahead. Let's try to answer this. It's very easy. The 12th question. I want everyone to answer this. For an element with atomic number Z is 30, what is the value of the atomic scattering factor in the forward direction? The condition is given as the forward direction. Forward direction means theta is equal to 0. In that case, what is the value of F? So we are talking about this particular value. Yes, Ahmed, very good. The right answer is option C. When we talk about the forward direction, the atomic scattering factor will be equal to the atomic number. Right. Let's go. Let's try to solve one more question. For which type of material is Compton scattering particularly problematic in the X-ray diffraction, leading to a high background? Okay. For which type of material Compton scattering will be particularly problematic? It means that the Compton scattering will be more. Okay. More problematic anyway. The background is always problematic for us, right? We want to remove that. Only certain cases only is there where we want to see the background. Okay. So it's a problematic, leading to the high background. In which case it will be Compton scattering will be high. So now let's not, without worrying about these things, we discussed that on what factor Compton scattering depend. So it is inverse to what the Thompson scattering depend. Okay. So if I am increasing the Z, so our Thompson scattering is increasing. Okay. So it means that if I, and same if I'm increasing the Z, the Compton scattering will decrease. Okay. The question is saying that they are getting high background. It means that their Compton scattering is high, which means that their Z is very low. Good. Yep, very good. The right answer is option B. Organic materials containing low atomic number elements like carbon and oxygen. Okay. This is the reason that if you add the carbon, yeah, very good, Chandrani. Yeah. If you add the carbon in your material and you try to do XRD, you will get a high background. The intensity of the background will be very high. Sometime people try to see from that perspective itself, okay, the carbon is there. Since the background is more, the carbon is there. Okay. So this is one way to see it. Okay. Again, it's not very characteristic because the Compton scattering is there. It's an elastic scattering. So option B is the right answer over here. Let's try to solve this. One more question I have. How do the intensity of the Compton that is incoherent scattering change with an increase in the ratio of sine theta by lambda. It's very easy, guys. We have discussed this a lot. Sine theta by lambda will it with increasing the sine theta by lambda. So we are increasing sine theta by lambda. This we are increasing. What is going to happen? Okay, forget about this. Let's talk about the Thomson scattering. So for the Thomson scattering, if I'm increasing sine theta by lambda, that is I'm increasing this, it means that I'm going to the right side. What the factor we am seeing on the f, f is decreasing, right? So now similarly for the Compton scattering, if I'm doing the same thing, if I'm increasing the sine theta by lambda, it means that I'm increasing the f, right? So here, what will be the right answer? If I'm increasing the ratio of this, they are going hand in hand, right? This one is increasing, this is also increasing. So we can say that it increases. So the right answer over here is option C. Right? Very good. Let me know if any doubt in this. Remember that to answer this type of questions, which we have where we have to deal with the Compton, try to see the opposite effect is the Compton. Okay. Now the 15th. The primary goal of calculating so now let's talk about the Bragg's law before we discuss this. So what Bragg's law say? That constructive interference will occur if the path difference is integral multiple of the wavelength. Okay, which we usually write at n lambda equal to 2d sine theta. So this is a path difference which is created at particular angle, which is created. Okay, only at the particular angle what will happen that this will be equal to the integral multiple of the lambda, and you will see that okay, the condition is satisfied. You will see the peak, you will see the intensity. Okay, so the thing is that Bragg's law is a like it will say that okay, diffraction is occurring, but will this diffraction will have certain intensity also or not? Sometime it happen that okay, see, let's talk about the simple cubic. Let's say we have at the edge also orthonomic. Let's say we are talking about edge. So this plane is reflecting, and this plane is reflecting, and their wavelength, the path difference there is lambda. Right? They both are undergoing the diffraction. They will add up since the path difference is lambda. They are going to add up, and they are going to contribute toward the intensity. Now the next part. Sorry, why I made these things. Okay. I'll use this paper itself. This is what the example has been given in the class. Now this two thing I'll pull it and I'll make it that so that it's come to the center. This is I put it in this particular direction, and I brought it to the body center, and so this will also move. So what is happening now? This first plane is going to reflect. The second plane is also going to reflect. These two were having the path difference of lambda. The thing is that the plane came in between them, which is like the difference of lambda by 2. So now since the path difference is lambda by 2, it means that they are destructive interference. So they this 1 and 2 is going to nullify each other. The HA will be 0. This 3 and 4, like below this, there will also be the small thing, this particular atom, this particular plane will be there. And with that 4 thing, it will going to be cancelled out. So overall, we will get the zero intensity, even though the Bragg's law satisfy and lambda equal to 2 and it was happening, still we are getting the intensity to be the 0. Okay, so see, the entire thing is that here is that, first of all, to get the intensity, okay, like there is two things. One is the Bragg's law and one is the structure factor. Okay, a structure factor is something which we are going to discuss. Okay. Bragg's law will tell whether the diffraction will occur or not. Structure factor will tell, okay, if the diffraction occurred, will that will that theta, will that particular angle have, will that diffraction will have intensity, whether it's having certain intensity of I or it's having the intensity of theta, it will be determined by the structure. So even though the diffraction condition has been satisfied by the Bragg's law, if the structure factor is telling that, okay, due to the arrangement of the atoms, it is the intensities are cancelling out each other and the diffraction is like the destructive interference is happening. Not only this, like even if the intensities are, sometimes we see that the intensity is somewhere at certain position we see the more intensities and certain we see the less intensity. Even if someone made some modification in the material, they can make sure, they can also make that this particular intensity will go high compared to this one. While the first case should be like, let's say the normal case would be the one, this is the abnormal case. Something, some modification they did, some texture they made. So this is going to enhance. So it's entirely depending upon which peak will have how much intensity, it will determine by the structure factor. Okay. Also, a couple of factors are there. The structure factor is one of the most important factor that is going to be contribute, that is going to affect our intensities. People do a lot of refinement and all, intensities and all, so that to match that intensity with the literature which was happening, so that this intensity is carrying the information about the position of atom. So for example, here what we saw that, here we saw that when the position of the atom was like this, we were getting the certain particular peak. While if I change the position of an atom from this particular configuration to this particular configuration, what is going to happen that my intensities, there is no intensity, there is only background, which was over here, it came to over here. So once I change the position of an atom, it is going to affect the atomic position, it is going to affect the intensity. Again, we are still not going in depth. The structure factor is yet to be discussed in the next week, and we are going to explore it more and more. Okay. So based on the concept that we have learned, this question number 7 which was left over, let's try to answer that. What is the fundamental reason that Bragg's law is considered necessary? It is necessary, but not sufficient condition for to observe the diffracted X-ray beam. It's necessary. The Bragg's condition should be satisfied. That is necessary. But whether that after satisfying the Bragg's condition, will that particular peak will have certain intensities or not, or how much it will have, that will be defined by the structure factor. Okay. So now let's say that the diffraction is not happening. The Bragg's law is not satisfied. There is no need to discuss the structure factor itself. So Bragg's law is necessary. If Bragg's law will not happen, if the Bragg's condition is not satisfied, you won't see peak at all. No. The Bragg's law is satisfied. Now that diffracted beam, whether it should have some particular intensity or not, it will be determined by the structure factor. Okay. So Bragg's law is a necessary condition, but not the sufficient condition. It's a necessary but not sufficient. Now the reason, the why it is the case. Let's see the reason. Braggs law only applies to the non-crystalline material. Braggs law does not account for the atomic arrangement within the unit cell, which can cause the destructive interference. Okay. See, Braggs law required a monochromatic X-ray beam, which is difficult to achieve. No, it's not about the monochromatic and all those things which we have already got. We don't have to discuss this further. Bragg's law only predict the wavelength of the diffracted beam. No, we are not talking about the wavelength. We are keeping it fixed. Okay, very good. Yeah, so Ritu has answered it. Option B is the right answer over here. Okay. So Bragg's law is not taking into account the atomic positions, atomic arrangement. Okay. Bragg's law will only tell you at what theta you are going to get a peak. Now whether this peak have intensity or not, that will be decided by the structure factor. Okay, again this thing we are going to discuss in detail. There was one more question left. Let me see. Yeah, so let's try to answer this last question. The primary goal of calculating scattering from a unit cell is to find out how the diffracted beam intensity depend upon. The primary goal of calculating the scattering from a unit cell. That is, we are talking about the structure factor. To find diffracted beam intensity depend upon what? Yes, very good, Gitu. Yeah, very good, Chandrani. The right answer is option C, the position of an atom. The intensities is very important. You will realize when you try to do the diffraction, when you try to analyze the things, when you try to analyze your the material, whether it's having certain defects or not. Let's see. You take a material, put it in the TM and pass a very high beam of electron through it. What will happen? It will create a lot of defect within the material. Okay, because you are impinging, you are forcing a lot of energy onto the material. So what will happen? That the defects concentration in the material will be high. Now that is going to affect your atomic position. So now if you take the XRD before you do this thing and after you do these things, you will see that there will be some changes will be associated with your intensities in the XRD pattern. Okay. So there is a lot of studies. So the entire liquid refinement thing, it depend upon the how good you are able to match your intensity, how good we are able to match your patterns. Okay. Okay, so this was all from my side for today. I would like to ask you, do you have any doubt? Then we can have a further discussion, or else we will find out. Okay, great guys. So I'm very happy that even though we changed the timing suddenly yesterday, tomorrow I have to go somewhere, and the information I got yesterday itself. So that's the reason why I was not able to tell you last time. I'm happy that still you guys are able to join. This is very great. Okay, so next time I'll you just keep on having the look on the announcement panel because it might be changed. There might be the possibility that the change might be there. And if the change in the timing is there, it will be the same, the Friday 6 to 8. If not, then the Saturday we'll meet 3 to 5. Okay. Okay, guys. Great. That's all from my side. Bye bye. Take care.